Sir, I think we are done with fourth chapter, sir. Can we start with fifth one? Okay. Mhm. Yes, sir, please. Yes, sir. Can we start? Mm. Yeah. Okay. So this chapter, which is together in IGCSE. Okay. So this is kind of last, but we have one more chapter of what we call it as a classical mechanics. Okay. So so what is the object is addressed in first chapter. When it is moving, how it is moving, addressed in second chapter. What is velocity, what is acceleration, and thing. Why it is moving is explained in third chapter. Okay. Um, what is the source of the movement is explained in fourth chapter. Forces, density, and pressure. Okay. So as move from one place to another place, so what happens in the process of energy of the object is what we will discuss this chapter, fifth chapter, work, energy, and power. Yes, energy of the object. What happens to so we will discuss what happened, what is literally happening when you move object from one place to another place, and what's been given to the object, that is energy. As a result, um, so it can be delivered as a force, it can be delivered as a acceleration. Okay, so now we just wonder what is the energy difference in 2 points and at what rate. Yes, at from 1 point to 2 point. Okay, so for example, this is point A and this is point B if the object is moving. So in first chapter we will discuss about what happens to the difference in velocity. So first two chapters. Second chapter, what happens to the difference in acceleration. Now we will talk about what happens to the difference in energy. So that's what we talk here. And how quickly the energy is supplied. That's what we call it as a power, rate of energy supply. Okay. So before going into the chapter, we should understand what is energy. Okay. So energy is ability to do work. Okay. So it's measured in joules. It can be measured in electron volt. It can be measured in so joule. Without goes it, saying it goes. It can be kilojoule, megajoule, or microjoule, millijoule. Mm. So electron volt for measuring energy of the order of 10 power minus 19. Um, so also, so we know that energy is base unit are so energy is base units or it's so force into distance. So kilogram meter square second power minus 2. Okay, so we already established, I think it doesn't matter what type of energy it is, it will always have these units. Kilogram meter square second power minus 2. Yes. Okay, whether it's a kinetic energy, whether it's a mechanical energy. What's the beauty is, even if the energy involved in wave, which we will not study here but little later, that also carry the same unit. And we understand wave does not have mass. But still the energy includes kilogram mass. So that's a beauty. Okay. Yeah. So we really do not worry or carry the information about what type of energy it is. As long as it's energy, then we go with this unit. That's all. Okay. And first thing we should understand, energy and work done, they are same. Okay. So they are very different in a higher, very higher level of physics. But for our case, it's same. We can consider them as same. It can be example like there is a person called Jane, and he is a human, or she is a human. Okay. So human is Jane. Jane is human. So work done is one type of energy. That's all. Yes. Okay. Like no, same. That's why we don't care what type of energy it is. It's same. Okay. Um, yeah. So this understanding is very important to study about energy, work energy and power. Okay. Yes. So okay, we can start with, so what is work done? Work done is force multiplied by distance. Okay. So what do we mean by this is, let's say there is an object, and if we are giving 1 Newton force for distance of 1 meter, okay, or we give F Newton force for the distance of d meter, then the work done we spend is 1 F Newton into d meter. So this is FD, Newton meter. So that's one more unit for energy. Okay, so energy is measured in Newton meters. So how much is 1 joule if you ask? 1 Newton force is applied for 1 meter. That's 1 joule. Okay, that's the idea. Now, so we established energy and work done are not so different. Okay, so if you give energy, or if we do some useful work on the object, then that is work done. That's all. So whatever we are giving is work done. Okay, and this can work on the object in different ways that we will study. For example, if there is no friction between this box and the floor, whatever the energy you give is going to utilize in the acceleration of the box. Sometimes you give energy, still the box is not accelerating, just moving. That's because there might be a friction between the box and the floor. Okay, so that also we will note down in this case. So the energy being utilized in different types or ways on the object. Yes. Okay. For example, let's say that I gave 5 Newton force. Okay. So we'll do a small example that here is a distance of 10 meter. Okay. And here is a box. In case one, no friction. Okay. So if I give 5 Newton force, and this 5 Newton force is, let's say that the object is 1 kg. And first case, no friction. So what will be the acceleration? No, give in terms of force, mass into acceleration. So acceleration is force by mass. So it's 5 by 1. So it's going to accelerate with 5 meter per second square. And it's going to slide through all the 10 meter. Okay. Now, in the second case, let's say that there is a friction. Now, friction is also a force, right? So it's going to consume some energy. Now, let's say that the friction between the box and the floor is 2 Newton. Okay. So now, if you give 5 Newton force, so there will be friction that will consume 2 Newton. So your resultant force will be only 3 Newton. So the object will accelerate with 3 Newton divided by 1 kg. So 3 meter per second square. Yes. Okay. So the idea here is friction also consumes some energy. So remember, we give 5 Newton, meaning that we are keep on giving 5 Newton force all the way it crosses this time. It's not just we give 5 Newton push. We constantly push around 5 Newton. Okay. Now, if you just give 5 Newton, in this case, friction, eventually this 5 Newton will be consumed by the friction, right? And it will end here. Okay. Is it clear, sir? Yes. So the last point we want to recall here is conservative forces and non-conservative forces. Okay. Small example is, let's take one object here. Okay. So now mgh is 0. It's close to ground. Now, if you move some distance, you will have some different mgh. Let's say 100 joule. Okay. And if you drop the object, it will reach the ground with kinetic energy of 100 joule. Okay. Yeah. So this is without air resistance. Okay. Then we call this as conservative field, conservative force, because it doesn't matter which way you move this. When you drop it, you will still get 100 joule. But if you account air resistance, then let's say that you move to 100 joule. When you drop it, when it reaches the ground, it will not exactly exhibit 100 joule of kinetic energy. Some amount of energy is consumed by air resistance. Okay, so this case it's not a conservative, because what's been given is not what you got. Okay, but the total is same. How the total is same? The kinetic energy you got in the ground plus the energy you lost due to friction. This will be give the total energy. Okay, so this is what we call it as principle of conservation of energy. Okay, and this idea is very important, principle of conservation of energy. Okay, yeah. So total energy input will be always equal to total energy output or consumption. Okay, but the useful output we get will be less, because you will lose energy in friction, you will lose energy in air resistance, you will lose energy in light, you will lose energy in sound. Okay. So what we get as an output is different from what is the total energy consumed. Maybe we can use consume. So consumption is very suitable word. Okay. Now, do you know about perpetual motion, sir? Have you heard? Perpetual motion. Okay. So perpetual motion is, for example, if you take a giant wheel and then collect water bottles here and fill the water bottles with half liquid, and once you start rotating, it will keep on rotating. That's the aim. No, it's not true. Okay. Yes. So or okay. So if you have a like U shape and you have a bowl here, and if you drop a let's say marble here, it will roll around and then jump back. Okay. So it should keep on going. That's what perpetual motion is, but it is impossible because you will always lose some energy in friction. And the thermodynamic second law forbids it. You cannot have perpetual motion. Okay. But if you calculate all the energy lost, that will be equal. Yeah, we have, yes, everything. Okay, even if there is a magnetic field that obstructs our motion, then we have to calculate that also. Okay, so now so let's say that um, in the conservation of energy, it is very important to understand how much we give. Okay, given energy, and how much we got useful output. This word is very important, useful output. Okay, so the idea is the useful output will be always less than the given energy, because of the friction, air resistance, whatever, blah blah blah. And let's say that we are using motorbikes, right? So we are burning some amount of fuel, but we receive energy in the form of many things. One of them is sound from the silencer. Still, that is a waste of energy according to us. But by nature, it's just even. So we have to calculate everything, and the ratio will be never one. They are never equal. Given energy will be never equal to total useful output. Okay, so it should be always less than one. So the efficiency of the system is total energy output of useful. Okay, so this is useful divided by total energy input, 100%. Okay, so in case if you have any doubt in efficiency, what is up, what is down, this number should never get one. It should always less than one. So the bigger one should be in denominator. Okay, so you can remember in that way. Yes. Now, what do we mean by a system is 50% efficient, 60% efficient? Meaning that if you give 100 joule of input energy, the system gives back you of what is your desired outcome. That is 60 joule. Then it is 60%. Okay. So how do we calculate what are the energy we give? Um, what are the energy we receive as a our desired way? In the sense, for example, if I am burning petrol, means my desired way is only I want to move through the motorbike. I don't want to give light, I don't want to give sound, I don't want to give friction or anything. Okay, but that's not that's impossible. It will always have some sideways to do. Okay, that's what we learn in a Skanky diagram in IGCSE. Yeah, efficiency diagram. So if we give 100%, only less than, so remember, the useful output is always less than the total input. Okay, so the efficiency never equal to 100%. So it is always less than 100%. Okay, it's not less than or equal to, it's always less than 100%. Okay, so by design we cannot get 100% efficient. Yes. Okay, is it clear, sir? Yes. Okay, so there is one exceptional case to this, that is energy mass conversion, that we will study in nuclear in A level. Okay, there is a possible way that we just take a small amount of mass and 100% we can convert into energy. But can we use that 100% energy? No, we cannot. Okay, that's a twist. Yes. Okay. Yes, please. Mm. Mm. Yes, yes. Mm. Transformers can be, in transformer, what you are doing is power. Okay, in transformer, if you take this side power, that should be equal to that side power. You can step up voltage, but the same amount you have to step down the current. So you just increase the yeah, increase the voltage and decrease the current, or increase the current or decrease the voltage. So we cannot increase both. Okay. Yes, sir. Yeah. Yeah. Okay. So that's efficiency. I think efficiency level problems are IGCSE problems. We do not need to do it here. Yeah. Yes, sir. Okay. Sir, efficiency, they don't ask us a direct problem, sir. They will be part of some other problem. Okay. So lastly, we have to discuss power. Power is rate of energy delivered. Okay. So power is energy by time. Sometime you have to use this equation to find the energy. Energy is power into time. Okay. So power has the SI base unit of its energy by time. So kilogram meter square second power minus 3. Mm. Or it can be power is given as uh, joule second inverse. Yeah. So energy is joule, power time is second. So power is joule second inverse. Okay. So this is defined. Yeah, yeah. SI unit of power. So 1 joule per 1 second is what we call it as 1 watt. Okay. So what is 1 watt is 1 joule is given every second. That is 1 watt. If 10 watt means 10 joule is given every second. 100 watt means 100 joule given every second. Mm. Okay. Yes. Now, so power is energy by time. We also know energy is force into distance, right? Yeah. So now instead of energy, I can write force into distance divided by time. Okay. So I can rewrite this force into distance by time. What is distance by time? So power is also force into velocity. Okay. So it can be measured in Newton meter second inverse also. But this is not SI base unit. Okay, sir? You just should remember. Okay. Yes. So using power actually can stir up the problem levels a little bit. For example, remember we did this Da Vinci design of propeller. So it's constantly going with 25 meter per second. Uh, do you remember that question, sir? So some question in the summer paper. Yeah. So you can refer as 25 QP11. Mm. So in that 12th question. Okay. Yeah. So so we'll work out power problems, but these are the things that we have to understand what is there in power. Okay. Now let's say that I give 50 Newton force constantly so that this object moves 25 meter per second upward. Now what is power used? Power is force into velocity. So 50 into 25 meter per second. Super. We gave 50 Newton power, sorry, 50 Newton force. Then only it is moving by 25 meter per second upward. Okay. So, yes. Okay. So if this velocity is not given, then first we have to subtract the weight and we have to work for the resultant force. Okay. Is it clear, sir? Yes. So in the end, we will solve problems related to power, sir. Yes. No, 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 no. We are far from that one. We have 1 minute. Okay. So this power and energy, this comes in different ways, sir. So this comes in electrical also. In electrical, okay. So voltage, current, and resistance are given, and time consumptions are given. Okay. Power consumed, so energy consumed in electricity is IVT. Okay. So power is, we know that energy by time. So it will be IVT divided by T. So it's just V into I, or I into V. Okay. So also you can, instead of V into I, you can use V equal to IR equation. Then you will get power is also I square R or V square by R. Okay. So in nuclear energy also, energy is MC square. Okay. So we will study what's energy stored in the spring later. But still I'll give, so energy stored in the spring is half Fx or half Kx square. Okay. So we will come across this energy and power over different topics until A level also. Okay. So what's the energy delivered in nuclear reaction, that we will wonder. What's the total power output of a star, that we will study in 25th chapter, astronomy and yeah. So we just have to remember the basics. That's all. Okay. Yes, sir. That's 5.1. So we have one more topic in this chapter, that is 5.2, gravitational potential energy and kinetic energy. Yes. Okay. So now let's take one example, that here is a box here and it's been moved to the height of h. Okay. Now we know that work done is force into distance. Okay. So against which force we are moving? Against the gravity. Precisely weight of the object. Again, weight of the object only we are moving, right? So what is the weight of this object in this case? If mass is m, mg. So weight of the object is mg. Moved by what distance? So the work done is mgh. Yes, that's gravitational potential energy. Okay. Now the gravitational potential energy, what is very important is, let's say that this is the ground. Okay. So if I move from here 0 meter to 10 meter, I will have a difference in gravitational potential energy, right? Let's say that I am moving from 5,000 meter to 5,010 meter. Still I will have the same difference in potential energy, because difference in height is same. Okay. This works close to the surface, because we will learn in a higher degree that as you go away, the gravitational potential, there is something called the gravitational potential, that increases over time. Oh, sorry, over distances. Okay. So change in energy is just change in distance. That's what we want to convey here. Yes. Okay. So that's why we always interested in change in gravitational potential energy, which is mg into change in h. Okay. So this equation is very important. And this equation gives us shortcut to many problems. Okay, for example, 1 kg object is dropped from 100 meter. Okay, what will be the velocity when it reaches the ground? Okay, that's a question. Now, if we do not know this energy chapter, we will work the we will work the equation of motion. We will find the time, then we will find what is the velocity, right? Now here is a shortcut of conservation of energy. We know that whatever the potential energy it has, that potential energy is going to be converted into kinetic energy. So we will just find the initial potential energy, which is mg into h. So 1 into g, 10 into h, 100 meter, will be equal to 1000 joule. This 1000 joule is going to be given as kinetic energy. So 1000 joule, yes, is half mv square. So we already know. So actually, instead of 1000 joule, we can write it as mgh. Okay, so that's very easy. 1 into 10 into 100. So 1 into 10 into 100. So 10 meter per second square, 100 meter, 1 kg. Okay, is equal to half, again 1 kg into velocity square. So now what we'll get? So 1 and, yeah, in this case 1 and 1, so we don't care. But actually, if we write mgh, it'll be very useful. So 2 into 1000, 2000 is velocity square. Okay, and if you look at the unit, so kg and kg got cancelled, right? So here what we have is meter square per second square. Here also meter into meter, so meter square per second square. So they will also perfectly cancel. Okay, so the homogeneity of equation, whatever we have left side, that should be equal to right side. So we will be square root of 2000. So what is square root of 2000? No, you can write it as 2 into 10 power 3, or 20 into 10 power 2. So 14 approximately. 40? 44. Yeah, we can call it as 45 meter per second. Okay, this is a shortcut. So what's the equation utilized this? Mgh is half mv square. Okay, yes sir. Now, yeah, is there anything to be given here? Okay. Yes sir. That's all. That's all in the topic of gravitational potential energy and kinetic energy. Now, let's say that we have to throw an object to infinity. Yeah, in distance. So that means that we want to throw it out of Earth atmosphere. So we want it to leave the Earth atmosphere. Okay. So can you see that mgh is half m square? Both m are equal. So we can cancel m and m. So directly you can find the v square is 2gh. So v will be square root of 2gh. So you can directly use this equation if h is given. Yeah. Okay. Now what's the beauty is, let's say that I'm throwing 1 kg mass object and 10 kg mass object from the same height, 100 meter. So what is the velocity they will reach in the ground using this equation? Same, because it is independent of their masses, because mass get cancelled. Yes, same time. They will reach same velocity. Yes. Okay. Say they will reach ground in same velocity, but If there is air resistance, the difference in density causes a different problem. So that's why, uh, yeah, in vacuum, if you drop a feather and a iron ball, they will meet the ground in the same time. Okay. Yes. Yeah. So throwing infinity is involves different information that we haven't covered so far. But this is the idea. Okay. Yes, sir. So yeah, that's all the fifth chapter. Uh, yes, sir. We'll do some problems, sir. Mm. So first we will do problems in energy. Okay. So here is a question in 9702 11 MJ 13. Okay. Question number 18. So a wind turbine has blades that sweep an area of 2000 meter square. Okay. Okay. This wind blade is sweeping this area 2000 meter square. It converts the power available in the wind to electrical power with efficiency of 50%. Mm. Yes, yes, yes. So the wind turbine will circle, right, sir? So this area is 2000 meter square. Okay. It converts the power available in the wind to electrical power with efficiency of 50%. Okay. Now the question is, what is the electrical power generated if the wind speed is 10 meter per second? Let's say that wind is approaching with 10 meter per second. Okay. And density of the air is given as 1.3 kilogram per meter cube. Do you understand the question, sir? So, so windmill is like this. Air is coming with 10 meter per second, and density is 1.3 kilogram per meter cube, and air. Mm, okay, and these plates cover the area of 2000 meter square. Okay. Now the efficiency of this windmill is 50%. Now the question is, what is the electrical power generated? Okay. Yes, sir. I'll give time. Yes. Okay. I'll give the clue, sir. Mass of the air is not given. Instead, density is given. This side area is given. Okay, okay, okay. Please do that. Please do that. Do that. Try on your own. Yes. I'll give the options also. Four options are there. 130 kilowatt, 650 kilowatt, 1300 kilowatt, and 2600 kilowatt. Mm. Okay, so super. So first I'll give the clue, sir. I want you to really figure out this. Okay, so first take a density formula. Density is mass by volume. From this, deduce what is mass. Mm. It's okay. It's okay. So rewrite this equation. Density is mass by volume. Instead of that, um, so from that get mass. What is mass? Density into volume, right? Mm. Since this volume, um, rewrite this volume into area into length. Okay, now you get mass is density into area into length, right? Mm. We already seen in this case, somehow if you divide length by time, you will get velocity. Okay, so find which equation you can put. So this mass into length, somehow. Okay, just try. Give it a try, 1 or 2 minutes. How to get velocity out of this? It's very simple. It's very simple, sir. Okay, sir. Remember, we are not talking about air constant air mass. What this air does? No, the air is moving towards the windmill, right? With some quantity. What quantity it's moving? One of the quantity of the air is density. What is the other one? Speed. That is length by time, right? So try to incorporate an equation instead of length. If you figure out length by time, you will do. Take your time, sir. Just take your time. Mm. You figure out, sir. But we do not need to know. That's the idea. Okay, you can take it 1 second. What question is asked? What is the power output, right? Okay. What is the power output? What is power? So power is super. Use the word energy transferred by time. Okay. So you are in the quest to figure out the energy. So energy, what formula you have used? What energy is being transferred here? But mgh is with respect to potential, right? But we were talking about moving object. Air is moving. The kinetic energy of the air only utilized to generate electricity. Is the potential energy of the air or kinetic energy of the air? So we have to use half mv square formula. Still the problem persist. M is there, right? So we have to find power. So naturally you write power is energy by time. So half m v square by time. Okay. Now instead of m, we know that density is mass by volume. So right, mass is density into volume. So density into area into length. Okay. So now instead of mass here, write this. So power is half into, instead of mass, density into area into length divided by time into velocity square. What is length by time? Velocity. There is already one velocity square. So you just make it velocity cube. So density into area into velocity cube. That's power. Okay. So half into density is 1.3 kilogram per meter cube into area 2000 meter square into velocity cube 10 meter square by 10 square is 100 meter square per second square, right? So look here, meter square and meter square here. Sorry, meter square and meter cube. So you will still have a meter, and here is 1 meter, here is 1 meter square. So we will get meter, here is kilogram. So kilogram meter per second square divided by uh, yeah. Mm, How much you got? 6500 is far from the actual answer. Yeah, 6500 is have you got for this one? Yeah, you. Mm, okay. Okay. Mm, yes. Yeah, you will get. So, but do you understand why we can consider time as one? Be- yeah, because air is moving with 10 meter per second. Okay, in 1 second, how much it will move? So, in 1 second, how much it will move? So, if you take time 1 second, then you can figure out the equation 10 seconds. Because what is power? Energy divided by second. 1 second, in 1 second, what is energy delivered? Yes. So, okay, so check this calculation. Half into 1.3 into 2000 into 100. So power, so this is the power given from air. Okay, so 1300, 4 zeros. Yeah. uh, mm. So this is the input. So this will be 133. We can take it kilowatt. Okay, and there is an option for this, right? So if you choose that, will be wrong. Yes. So because efficiency is so output by input uh, into 100. So this is 50%. So we want output. So it will be input, which is this 130 kilowatt multiplied by 50 divided by 100. 650 kilowatt. Sir, this would be 1300 kilowatt, not 130. Check the math. This would be 1003. Yeah. Just check this calculation, sir. How much? What's the equation? Hmm. Hmm. Yes. So 50 by 100. So you will get 65,000, right, sir? 65,000 watt. Uh, no, but I think we are off by factor 10. Figure out where we made mistakes, sir. Because we have 650 kilowatt, but this is just 65 kilowatt. Did we miss any? Uh, 10 into 10, 100, 2000. One minute, where's my calculator? Yes. Okay, it's 0.5 into 1.3. Is there any SI unit? Kilogram per meter cube, meter square, kilogram, 10 meter per second. Yeah, density is given in kilogram only. This is also given in meter per second only. Sir, here is a mistake. So this is supposed to be V square, V cube, right? Okay. So I just explained the problem, sir, again. So very simple. So we have a windmill whose blade sweeps an area of 2000 meter cube. So air inbound with 10 meter per second of density 1.3 kilogram per meter cube. Okay. And the efficiency of the windmill is 50%. We have to find what is the total output we get. Output power. Okay. Now we know that energy is half mv square and we want power which is half mv square by t time. So by 1 second. Okay. So we know that density is mass by volume. So mass density into volume, density into area into length. So we can write power is half instead of mass density into area into length into velocity square divided by 1 second for time t. So this L divided by 1 second is V. So it's supposed to be V cube, right? So half, yes. Area into length. Okay. Yes, L is distance. Yes, it's not yes 1 second. Distance by time, which is velocity. Yes. So half into rho into. Is it clear, sir? So it's velocity cube. So half into 1.3 kilogram per meter cube multiplied by area 2000 meter square into velocity cube. So 10 cube, which is 1000 meter cube by second power minus 3, right? So meter cube and meter cube will get cancelled. You will get 0.5 into 1.3 into 2000 into 1000. So what you will get is 1300. Yeah, 5 zeros you should have. Okay. So you can write it as watt. So kilogram meter square per second power minus 3. That's watt. So we can write it as 1300 kilowatt. Okay. So there is an option for 1300 kilowatt. So if we choose, we are wrong. See. Mm. So what we can do is, yeah, so uh, output output by input multiplied by 100% is efficiency. So we want only output is efficiency in percentage multiplied by input divided by 100. So 50 percentage into input 1300 kilowatt divided by 100. So you will get 1.3 into 50. So 650 kilowatt. That's our output. So option B. Okay, sir. See, very interesting. Yes, but places like, so most of the energy question, they will not give directly the time. If you are finding power, you just have to assume what is power. What is the definition of 1 watt? 1 joule per second. So you just assume time is 1 second. Okay. So it will help you in lot. Unless until the time is given explicitly, if you want to find the power, you can just assume in 1 second how much energy is transferred. That's the question. So you just find the energy transfer per second is power. Is it clear, sir? Nice question, bro. Yeah. Okay. So we'll do next question. Okay. Most of the energy questions, they are from either electrical or spring. Okay. So the same paper, question number 19. Okay. So here is a wheel. No, but I think we didn't cover enough. No, no, we didn't cover enough theory to solve this problem. So we'll go to next problem. So it involves next chapter topic also. Okay. So here is a question. So this is question number 17 in 9702 12 MJ 13. Okay. So the train on mountain railway is carrying 200 people. Okay. 17, sir. So 200 people, average mass of 70 kg. One person mass is 70 kg. Average mass. Okay, sir. Up to a slope of an angle of 30 degree. Now here's a twist. The horizon, okay, speed is 6 meter per second. Train is going with the speed of 6 meter per second. The train itself has a mass of 80,000 kilogram. Mass of the train, 80,000 kilogram. Okay. The percentage of power from the engine which is used to raise the passenger and the train is 40%. So efficiency is 40%. Okay. So what is the power of the engine? So can you see that this time they are asking the input? Hmm. Yes. I think you should work. Please try to work this out. Mm. Sir, by the way, four options are there: 1.1 megawatt, 2.8 megawatt, 6.9 megawatt, and 14 megawatt. First, working out the sine theta, sir. Sorry, theta. Yes. Okay. Ah, yeah, yeah, no problem, no problem. Work it out, work it out. No, you can just simply draw the triangle and find it, sir. Now this is 6 meter per second. What you want to find? Horizontal. Now this is 30 degree. Now horizontal is cos 30 into 6. Vertical is sine 30 into 6. Mm, close. Did you work out the efficiency part? Okay. What you worked with cos theta or sin theta? And you used velocity square. Okay, okay, okay. Mm. Sir, okay, okay. Hmm. So here is the problem. This 9.81 is G, right? So if you want to find the force with mass, if you multiply it by G, acceleration due to gravity, you are talking about gravity force, right? What is the job of gravity force when you move horizontally? Ah, okay. Try again, sir. Try again. We do not need to find the force. What is the power of the engine, right? Try using mgh or half mv square. Force also we can find, but it's too long. Try using half mv square or mgh. Mm. Sure, sir. You found the answer, sir? Yeah. Tell me what's the answer. Okay. Okay, you used half mv square or mgh? No, sir. Yeah. Okay, no problem, sir. So now let's consider this as a train as a single object. Okay. So check with this. What is the total mass of the train? 200 people are on board. So 200 into 70 plus train itself is 80,000. So how much is this? 94,000. So 94,000 is mass of the train. Okay. So we need to find the power. Power is energy by time. Okay. So now velocity is given 6 meter per second in this direction. Now we can find the horizontal velocity and vertical velocity. Okay. So sorry, component. So it's easy for us to use mgh in this case. Okay. I'll tell you why. Now, what is the vertical component of the velocity is, if this is 30 degree, then this will be sine 30, right? So, sine 30 into 6. Now, let's take velocities sine 30 into 6. Okay, sir. Now, energy is mgh. Mgh divided by time. Now, this h divided by, yes. h divided by time is velocity. So we can take it as mgv for energy by sorry, power. Okay, so power is mgv. Okay, sir. Can you see that the force is m? Ah, yes. Ah, okay, okay. Watch here. So can you see that mg is force and velocity is here? So power is force into velocity. Okay. Now, uh, yeah. So power is energy by time. So mass is 94,000 into g is 9.81 into velocity is 6 into sine 30. Okay. So if we do this, what we are getting? 94,000 to 9.81. So we get 2761234 watt. Okay. What you are getting, sir? 94,000 kilogram multiplied by 9.81 meter per second square, 6 meter per second. Do this, try this again. Sine 30. And check if your calculator is in degree mode or radian mode. Yes. Mm. Super. Okay. Yes. Now this is output required. So output by in so I output by input into 100 is 40%. Now we want to find the input. So this is output by 40% into 100. So we have to do 276, 1, 2, 3, 4. Yeah, only 40, right? Yeah, divided by 40 into 100. So what you get is 6, 9, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Mhm. 1, 2, 3, 4, 5, 6, 7. Yes. Okay. So 6.9 megawatt. So option C. Okay, sir. That's why you should check, sir, actually. Yeah, that's why we should check whether it's in degree or radian mode. Hmm. Yes. Okay. So I think remaining we will solve questions when we solve the topic wise questions together. Okay. Yes, sir. Okay. So do you have some exam tomorrow, sir? Oh, I see. Okay. Okay. You take care with that. So we'll meet by Saturday. Okay, sir. I'll text you the timing by tomorrow evening. Mhm. Yes, sir. Yes, sir. So otherwise, do you have any? No. Do you have any other plan by Saturday? Oh, oh, I see. Okay, then. Okay, okay. Then take care of that one. We'll try to meet by Sunday, or again we'll meet Tuesday. Yes. No, no. What time you are free? Tell me what time you are free. Okay. So I will be available by afternoon, sir. So yes. So we can, if you want, we can have by afternoon or evening. Tell me which one you prefer. Evening. Okay. So then we'll have like 5 to 9 or something like that. Okay. So if you want to long, we can have it afternoon. If you want like 2.5 hour class, no, then we'll have it by evening. Okay. Ah, yes, yes, yes. Okay, okay. Okay, sir. Okay. Yes, sir. Then take care. Bye. Mm. Yes, sir. Sure, please. Mm. Thank you, sir.